Suppose we have a binomial distribution with 6 trials and the probability of success, which is p, is 0.7. Now the distribution for that would be, let's see, the success is 0 through 6 and the probability of r number of successes would be given here. And we know from the previous section how to make these calculations. It turns out that this relationship between the r and the probability of r is graphable, and we can know quite a bit about the distribution by looking at the graph. The graph we're choosing is a histogram, and here's the histogram corresponding with this information. Notice the r successes along the horizontal axis, 0 through 6, and the probability values along the vertical axis. And for 6 trials, probability of success is being 0.7. Notice that we have a graph that is skewed to the left. We have this smaller tail portion over here to the left, and the meat and potatoes of the graph are over here to the right. Now, and this is the kind of pattern that will emerge as the p-value gets larger and larger. The skew part will become longer and longer over here, and the larger humped region will be more and more to the right as p gets larger. And because after all, the probability of success is relatively great here. It's greater than 0.5. So no wonder there's a higher probability associated with 4 successes, 5 successes, you see, under this circumstance. And if the p-value, on the other hand, was something like 0.3, then the probability of 1 success or 2 successes would be much greater than the probability of other successes, you see, and therefore we would have a graph which had a high side over here and a skew over to the right. Okay. So that's just kind of the nature of the situation. What would you expect to happen if the p-value, the probability of success, was exactly 0.5? Well, you might think that, gee, that the high side will be in the middle. Well, it certainly will be, and in fact, the graph will be perfectly symmetrical. That is, the graph will look like this. So 6 trials, the p-value is 0.5, and the graph is perfectly symmetrical. Now, anytime the p-value is 0.5, the graph will be perfectly symmetrical regardless of the number of trials. And it turns out, though, that if there are many trials, that even if the p-value is a little bit away from 0.5, is a bit different from 0.5, the graph is going to look symmetrical if there are enough trials involved in the situation. Well, let's talk about mean and standard deviation. It turns out that with binomial distributions, the calculation is especially easy. Now, from before, now let's just relate this to what we had before. That mu before was the sum of the xpx values, and that sum then will give the mean. Now here, for a binomial distribution, the mean is simply NP, the number of trials times the probability of success. And that's really all there is to it. Now we could calculate the mean doing that, but it simply isn't necessary. There's just a very simple way to deal with it for binomial distributions. Now, the mean is called the expected value, and it is also referred to a lot of times as the balance point. And we can get the feeling for the balance point idea if we look at the examples that we had over here. Now, let's make the calculation for mean. We're going to look at standard deviation in just a minute, but let's look at the calculation of mean for our first distribution over here. It was 6 trials, the probability of success 0.7. So the mean is n times p, or 6 times 0.7, 4.2. So that 4.2 is the expected value involved in the distribution. And let's look over here and see why it's may be called a balance point. See, 4.2 is right in this neighborhood. And it's a balance point because it sort of balances the, if you think about area here, and we could indeed think of areas because these bars are exactly 1 unit wide, and if we're thinking about their area, it's base times height, or 1 times the height, and therefore the heights of these bars correspond with their probabilities, you see, with the probabilities associated with them, so we could indeed think in terms of that. But at any rate, 4.2 is the mean, and it's the balance point. So it kind of balances the areas you see on either side of that particular point. Just another way to look at the situation. The balance point here for 6 trials, 0.5. Now remember, it's just NP, so it's 6 times 0.5, half of 6, 3. So the balance point is right here at 3, and we can see that indeed it is a balance point if we think of those areas having weight or something like that. Okay, the notion of standard deviation. Now, when we talked about standard deviation before, we were presumably making a chart or looking at a chart or making the calculation on the calculator, but it turned out to be the square root of the sum of and all of this business. Okay, quite a calculation. It's quite a bit easier for the binomial distribution. It's the square root of NPQ. Now, N, the number of trials, P, the probability of success, Q, the probability of failure. And we know that P plus Q is 1, so these are easily figured from one another. And this is a measure of the spread of the information, as we know from before. And the actual calculation for 6 trials, P being 7/10 would be the square root of 6 times 7/10 times 3/10. The 3/10 is calculated as 1 minus 0.7, so 0.3. And when the smoke clears here, the standard deviation is approximately 1.12. Suppose a satellite needs 3 solar cells to operate properly, and suppose the probability of failure for one of those cells, for each one of those cells, is 0.15, and suppose the cells operate independently. Then we're setting up a problem here that we can solve. Now here's the outline of the situation. 3 solar cells are required. The probability of failure for the solar cells for each one of them is 0.15. Now we'd like to figure out how many cells are needed for the expected value of the number of working cells to be greater than or equal to 3. That is, for the average number. Now when I say average, I'm loosely, informally talking about the mean. So the mean number, we want the mean number of working cells to be greater than or equal to 3. And now here's the situation. N is the number of cells. P is the probability of success. Now if the probability of failure is 0.15, the probability of success would be 1 minus 0.15 or 0.85. Q, the probability of failure, is 0.15. R is the number of working cells, and mu is the expected value, the mean number that we're talking about here. All right, let's calculate that expected value to be greater than or equal to 3. Now what does that mean? We haven't really talked about it very much, but we know that mu is NP, and we would like for this mu value to be greater than, to be greater than or equal to 3. So if mu is NP, then NP needs to be greater than or equal to 3. And P, the probability of success, is 0.85. And N then needs to be greater than or equal to 3 over 0.85, or N needs to be greater than or equal to 3.53. And since we're talking about a whole number of cells, we can't have partial cells. We would probably say then that N needs to be 4 or larger than 4 for the average number of working cells to be 3 or more. Okay, here's another problem. Find the least number of cells needed to be 97% sure that there will be adequate power. Now, adequate power occurs when 3 cells are working. So, now let's see, adequate power. So what we'll do is, will there be adequate power? Are we 97% sure if there are 3 cells on board? Well, let's see. If N is 3, then the probability of all 3 of them being successful, you see that R is equal to 3, would be success, success, success. You see, so it'd be 0.85 cubed or 0.614. No, the probability isn't there. We're not 97% sure in this case. Now, I'm going to actually show you 2 ways to make this calculation. This is the most direct way to think about the problem, I think. If n is 4, now we're just picking off, well, what happens if we have 4 cells? What happens if we have 5? What happens if we have 6? We're just going to evaluate the situation according to the number of cells that we may have on board. If we have 4 cells, well, let's see. We can set up a little probability distribution according to 3 successes or 4 successes. Now, we don't need to worry about 0, 1, and 2 because we're trying to be sure that our satellite is going to operate, and the satellite only operates if we have 3 or more cells working. So we want the probability that 3 will be working and the probability that all 4 of these will be working. Well, the probability that 3 will be working is this. The probability of 4 is this. So the probability that r is greater than or equal to 3 would be the sum of these two, or 0.89. Well, we're not there yet. We don't have enough cells working or enough cells on board to be 97% sure that we're going to have power. All right, what about 5? Well, if we have 5, here's the distribution. For 3 of them to be working, here's the probability associated with that. For 4, for 5, so the probability that r is greater than or equal to 3 would be the sum of these, or this. So here we're then 97% sure, a little more than 97% sure if we're operating with 5 cells. Now, this is kind of a direct sort of approach. You can see how this situation could get out of hand, though, if in certain circumstances where we would have to investigate in many different distributions to see if the sum of so many of them comes up to a certain level. Well, another approach to this is sort of the backhanded approach, and it sort of works like this. It's the idea that if we want to be 97% sure that we have success, that we have an adequate number of cells working for power to be available, then what about the failure side? If the success side, if we want to be 97% sure that we have success, what's the failure side? Well, it's 1 minus 0.97 or 0.03. And we might take that approach for the calculation. That is, we're thinking of it mathematically like this. We know the probability that r is greater than or equal to 3 plus the probability that r is less than 3 is equal to 1. Or we can write it like this, that the probability of r being greater than or equal to 3 is 1 minus the probability that r is less than 3. Or the probability that r is less than 3 is 1 minus the probability that r is greater than or equal to 3. And we want this probability to be 0.97, 1 minus 0.97, 0.03. So we'd like for the probability of the number of successes being less than 3 to be smaller than or equal to 0.03. And then we could structure our tables, the tables over here, our distributions, so that we add the probability of 0 plus the probability of 1 plus the probability of 2. And we want that sum to be less than or equal to 0.03. And it works well with the calculator as well. We need to remember that we're calculating the accumulated probabilities up to a certain point here, and we want those accumulated probabilities to be less than or equal to 0.03. Now, we talked about the probability that r is less than 3. Well, to the calculator we need a less than or equal to idea, so we're going to use an r value of 2 because r being less than 3 is the same thing as r being less than or equal to 2. So here we go. Second VARs puts us into the menu, and here we want this accumulation function, and the n value is what we're investigating here, and we can investigate this at let's investigate it at 3. All right, so n is 3, comma, the probability, the p-value 0.85, and now the r value, that's the trick now, is 2. And now we want this accumulated probability of 3 things, the accumulated probability up to an r value of 2, that is an r of 0, plus the probability that r is 1, plus the probability that r is 2. We want that accumulated probability to be less than or equal to 0.03. And here's what it turns out to be when we have an n of 3. Well, we need more n's. We need additional n's. Now, let me show you how to get back into this function without having to go through the business of the second VARs and entering that menu. You can press second and then enter, and it will give you the previous item. And now we can use our cursor to go back up and over and actually change the value of n very quickly. So I'll change the value of n to 4 and then press enter. And here is the accumulated probability up to an r value of 2 given an n of 4, you see. And now we're not there yet. We need this number to be less than or equal to 0.03. So we'll go second enter, and we're back into it again, up arrow, over to the right, enter a 5, and enter. Aha, now the probability, this accumulated probability of an r being less than or equal to 2 turns out to be less than 0.03 for an n value of 5. The type of problem we just looked at falls into a category of problems called quota problems. And they occur rather often in everyday life. They involve such things as the frequency of medical checkups, the expected number of production flaws, the expected number of bad loans at a bank, number of satellite solar cells is what we just looked at, sales quotas fall into this category, and that kind of thing. Here's another such problem. The probability that a radar station will detect an enemy airplane is 0.65. How many stations are needed to be 98% certain that an enemy plane will be detected by at least one station? So the success rate of a radar station is 0.65. So P then is 0.65. Q1 minus 0.65 is 0.35. Now we want the probability of a radar station detecting, at least one of them detecting the enemy aircraft. We want that R value to be greater than or equal to 1. One, maybe more, stations are detecting the aircraft. We want that probability to be greater than or equal to 0.98. Now again, as in the problem before, we could take a rather direct approach and say, gee, do we have this kind of assurance if we have just 2 stations or 3 stations or 4 stations or whatever? And that process would work like this. If we're talking about having 2 stations, then the number of successes of stations that will detect the enemy aircraft could be 1 or 2. And, well, it could be 0, but we want that R value to be greater than or equal to 1. So we only need to write or calculate R being 1 or 2. And these are the probabilities associated with them. And so the probability that R is greater than or equal to 1 would be the sum of these, and that's not enough. If N is 3, if we have 3 stations, then R could be 1, 2, or 3. These are the probabilities. So the probability that R is greater than or equal to 1 would be the sum of those or this. We're still not there, though. This 0.958 is still not enough. We need more stations, so we would continue the investigation, presumably. Another way to approach this problem, and it's a way that's even easier than in the previous problem, is like this. We're thinking, well, if the probability of R is greater than or equal to 1, if we want that probability to be greater than or equal to 98% or 0.98, then the probability that R is not greater than or equal to 1, that is, the probability that R is equal to 0, must be less than or equal to 0.02, or 2%. You see, if it's 98% success, it's 2% failure. And we know that P is 0.65, so all we need to do is look in the table, and in the table in the appendix, and look at the various groupings for various values of n. You know, check out n equals 2, n equals 3, n equals 4. And all you need to do is look at the probability of 0.65 now, but look for an R being equal to 0, being 0.02 or smaller than 0.02, and then just look to the left on the page and look at the n value. That's really all there is to it. Another way to deal with this, and a way that you can do it on the calculator, is this. Since the probability that R equals 0, that's no successes now. That means failure, 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 failure for however many n's, however many we have for the value of n. If we have, if it's 5 trials, then the n value would be 5. So it's failure for all of the trials that we have in the experiment. So it would be q to the n power, or 0.35 to the n. And in this circumstance, we want 0.35 to the n power to be less than or equal to 2%, or 0.02. Now, how many does n need to be for this to occur? And you can just pop it into the calculator and just put 0.35 times 0.35 equals. All right, that's 2 factors. And then take that answer times 0.35, there's 3 factors. And whenever you see a value come up as the answer, to be less than or equal to 0.02, if you're counting factors, then you've got the number of factors necessary. It turns out that 4 factors are necessary. N is 4. 4 stations are necessary, 4 radar stations are necessary for us to be 98% sure that at least one station is going to detect an enemy aircraft. The Denver Post reported that a recent audit of the Los Angeles 911 calls showed that 85% were not emergencies. Suppose that the 911 operators in Los Angeles have just received 4 calls. The A part of the problem is asking us to find the probability that all 4 calls are in fact emergencies. Let's outline the information that we have. We're talking about 4 calls here, and there's an 85% of the calls are not emergencies, so we're defining success here as a non-emergency, and so the p-value is 0.85. The q value would be 1 minus 0.85, and that would be a call that calls that are in fact emergencies. So there's a 15% chance that the call is an emergency, 85% chance that the call is not an emergency. All right, now we can think about our problem. What's the probability that all 4 calls are in fact emergencies? All 4 are emergencies. Now we're defining success as a non-emergency. So if we're thinking about all 4 calls being emergencies, that's no success, no success, no success, no success. You see all 4 times. So the probability then of an R being 0 is what this problem is all about. And for R to be 0, it would mean that we're thinking about failure, 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 failure. So that would be a Q to the 4th power. Q to the 4th power means 0.15 to the 4th, or this very, very small decimal number, which is approximately 0.001. That's like less than 1/10 of 1%. So there's a very small chance of that thing happening. The B part says, what is the probability that 3 or more calls are not emergencies? Now, success is defined here as non-emergency. The probability that 3 or more calls are not emergencies means that we want the probability that R is greater than or equal to 3. And that's the same thing as the probability that R is 3 plus the probability that R is 4. And looking in the table for an n value of 4 and a probability of 0.85, we find an R value of 3 being 0.368 and an R value of 4 giving 0.522 for a sum of 0.89. So it's a rather high probability, you see, that 3 or more of the calls are not emergencies. Now take a look at this part of the problem and think about it with me. How many calls in would the 911 operators need to answer to be 96% or more sure that at least one call was in fact an emergency? Pretty interesting situation, and this part of the problem is the reason that I chose to work this problem with you. You know, we're thinking at least one was in fact an emergency, and at least one, when we see that in a problem, we want to write down R is greater than or equal to 1. But gee, R is not associated with an emergency. R is associated with a non-emergency. Well, let's begin our analysis of the problem like this. We're looking for an N associated with the probability that we have at least one emergency is greater than or equal to 96%. So we certainly don't need this N of 4 that we have used for the past parts of the problem. Okay, now let's reinterpret the probability that at least one emergency occurs is greater than or equal to 96%. Now, at least one emergency. The sort of the antithesis of that is the probability of no emergencies being less than or equal to 4%. Probability of no emergencies. Boy, that sure is inviting us. None of something, you see. It invites us to say R is 0 for none of something to take place. But gee, R is the idea of success, but success in this problem we've defined as non-emergencies. Now, if we could just define success as an emergency, gee, then we would have R being 0 for the probability value that we're looking for in this problem. Well, can we do that? Well, sure we can. We just redefine success. We just swap the percents associated with P and Q. Just change our thinking about the problem a little bit. Now that we have redefined success, we look down at the bottom of the screen now, the probability of at least one emergency. If an emergency is a success, then this is the probability of R being greater than or equal to 1. Is greater than or equal to 96%. Now that corresponds with, now what's the sort of the antithesis of that? The probability of no emergencies. Well, no emergencies would be an R of 0. So the probability that R is 0 is less than or equal to 4% is what we're looking for. And we can just look at the table for a particular value. 4% is 0.04. So we're looking in the table in the back of the book for an N associated with an R of 0 being less than or equal to 0.04. So you look back there, you look at various R equals 0 values, and you'll find eventually that N needs to be 20 for an R of 0 to be less than or equal to 0.04. So the reinterpretation of the problem is 20 calls would need to be received by the 911 operators to be 96% sure that at least one is in fact an emergency.